Today I'm going to present how to build a model with an effect compartment in Phoenix Win-on-Lin. I need to repeat some information about this series because we typically have new attendees who may not know. So with all sessions of the PML School that we've shown so far, we've taken examples from the Gabrielsson and Dr book, as you see here on the bottom as a frame. This is the exercise PD22 from that book, Effect Compartment II, intravenous infusion. And after this session, we will make available the textual model that we present and also the slide deck. This webinar session will be recorded, and I will post the link to the recording as well as the other materials on the Certara forum after the event. During this session, you can post comments and questions into the Q&A panel that is you see right on the right-hand side of the WebEx console. For simple questions, Chris Mehl will cover this and will monitor the Q&A panel. For simple questions, he will respond right away. Other questions we will cover after the presentation, and as we typically do, for all those questions, we will post written answers to our forum as well. Next slide. Effect compartment models are also known as link models. And some of you may remember that just a few weeks ago, we had a session with a similar topic. Dan Weiner was presenting on the analysis and comparison of a link, turnover, and a receptor binding model. So why do we need to repeat the link model here? As we said in the introduction to the PML School last year, we have analyzed all the modeling questions that we receive in support. And there are some popular questions that can be covered by this specific exercise, PD22, which are how to add an effect compartment to an existing PK model, how to combine an infusion model with a link model, or how to set up multiple doses for a link model. By now, we have gone through 14 PML School sessions. You may already have a good idea how to accomplish these tasks. But this exercise can really highlight the ease and the flexibility of the Phoenix model, how to deal with these slightly different scenarios in an efficient and straightforward manner. So this exercise is more about interacting with the Phoenix model interface, and it will not cover the topics that Dan already presented a few weeks ago, where the question was how to prefer a link model over a turnover model, or when to pick a receptor binding model, for example. So let me switch over. So the objective for today is to model response time data with a link model after IV infusion. We want to find estimates for the 4 PK parameters, as well as for 3 PD parameters, plus another parameter that links the PK and PD data, KE0, the rate constant for the effect compartment. Finally, what we also want to do is we want to simulate repeated infusion regimen with the target responses. Okay, and here's the problem specification. Volunteer was given IV infusion dose of 69,000 units, it must be micrograms, over 15 minutes. And plasma concentrations were sampled over 720 minutes, or 12 hours if you will, and the response measurements were done at the same time points. Let me go ahead. Okay, so this is, we first start typically with the exploratory data analysis. So here's the plot of the concentrations in blue and the response in red versus time. Okay. So what we see here is the typical peaks occurring for the concentration and for the response in a delayed manner. So the response is delayed with respect to the concentration. And we see the plasma concentration goes straight up to a peak after infusion, and then it declines rapidly and fallen down. And you can also clearly see the two slopes. This is a log scale for the concentration, the linear scale for the response, but you clearly see the two slopes for the concentration that hints towards the two-compartmental model. The response in red also rises very sharply, but the peak occurs a little bit delayed with respect to the concentration. The high values maintain for a while, the high response values maintain for a while, but then decline and falls more rapidly than the concentration. You know, on a first glimpse, when you compare these two curves, there does not appear to be any relationship between the concentration and the response. So this is first plot. For PK/PD data, we also want to look at the response versus the concentration, and here you see the concentration again on a log scale. And this shows the typical hysteresis loop. It starts here and swings up until it reaches a maximum, and then it falls down again as a downswing arm. And we can see the typical pattern that for a particular concentration, we have two concentration, which are just measured at two different time points with two different responses. And this indicates the temporal differences between plasma concentration and response. And this could be due to distribution of the drug from plasma to the site of action. And usually this can be modeled by a hypothetical effect compartment, which I will show you how to build on the next slide. So this is our built-in options in the Phoenix model object. And here what we need to do is to build the PK/PD link model. We uncheck the population box because we only have one profile. We change from PK type, the model type from PK to PK Emax. Stick with clearance, stick with intravenous, switching the number of compartments to 2. We uncheck the closed form because we want to deal with differential equations. And then here we need to activate the infusions box since we have as an administration IV infusion. And this is a new feature in Phoenix 7.0, the duration. You can either enter the infusion as a rate, which is the default and was available until 1.4. And now you have also the option to specify your infusion with a duration instead of a rate. So I check this on. Now we're coming to the very crucial step for the whole exercise, and that is, you see this tiny unimpressive checkbox called Effect CPT. That's it. If we activate this box, we are actually incorporating an effect compartment to the model. Okay, the rest of it is stays the same. For the response, we stick with the additive residual error model, and for the concentration, we switch to a multiplicative one, and you see the PML statements on the right, but let me switch to the next slide. So here we are just comparing the different representations of the PK/PD model. Here are the built-in options, and a graphical representation is this picture here in the middle. And this illustrates why this model is also called a link model. You see the PK block, PK model here on top, and the PD block at the bottom, and the effect compartment is just a link between the PK model and the PD model. The whole thing in PML code looks like this. A pretty long code, but we know that we can get rid of all these structure parameter statements because we are only having fixed effects that will reduce the number of lines, but we come to that on one of the next slides. And since model building was so easy and quick, and actually we call this series PML School, I want to show how the model equations are represented in the PML code in more detail. And I also want to show you how to implement a couple of options that might be of interest. So let's switch to the next slide. Here are the model equations. The first one is the typical differential equation for a two-compartment model with IV input. So we have got the input IN, and typically we'll deal with amounts, drug amounts in PML rather than concentration. So we have here the construct volume times dc by dt. So we have the clearance in the central compartment and the clearance on the peripheral compartment. And we have an effect compartment in the model that links the PK model with the PD model. That is just the KE0, a zero order rate constant times concentration in the central minus the concentration in the effect compartment. And for the Emax model, we have just a typical Hill equation with Emax and slope factor gamma and the EC50 value. We don't have a baseline for this in this model. And when you compare these equations with the PML code below, I'm just highlighting these three entries in the code which refer to the formulas above in yellow. You see it's implemented as is. There's really no change. It's just written as is. Coming to a new feature in Phoenix 7.0, delay differential equations have become a very popular topic over recent time, and this seems justified since delays are happening very often in pharmacokinetics and pharmacodynamics, and we want to model delays in an efficient and easy manner. And with a new version of Phoenix 7.0, we have introduced this as a new feature to PML. So you can express a delay in a differential equation with a single statement. And that's what you see here. We just replaced the effect compartment with this statement. And here I'm using the formula CE. This is a delay statement. I'm using the A1. This is the amount of drug in the central compartment, together with a T lag parameter, a time lag parameter, which is a delay, and this whole expression is then divided by the volume of distribution to get to a concentration. And this should cover for temporal differences or delays between plasma concentrations and response. And with this statement, I mean, the whole model looks much cleaner now. And the effect compartment is really just a hypothetical construct. There is really no physiological counterpart to an effect compartment. So going forward, I would recommend using the delay statement instead of the effect compartments, and this is much more efficient. Before we start with the demo, here comes a further option, the textual model with explicit concentration. We can reduce the PK-PD model to a simple PD-Emax model. And we can achieve this by using explicit concentration values. For this data set, we have for each response measurement also a plasma concentration value. So this is possible. But in general, the assumption for modeling PK-PD data is that the PD data does not impact the fit of the PK model, since there are no shared parameters between the PK and PD model. And it appears as if the PK model only serves as a smoothing function to get predictions of concentrations at the times when you have response or PD data. So this smoothing is not required in our case, since in our data set we have a concentration value for each response measurement. So even if we have temporal differences between the concentrations and the responses, we can use explicit concentrations in our PED model. And this is the associated PML, right, where you just introduce the explicit concentration by the covariate statement, covariate CP, plasma concentration, and then you can use it in the differential equation for the effect compartment. And as you can see, this reduces the lines of code quite substantially. We only have one derivative, then the Emax model, the residual error model, and 4 fixed effects. All right. Next one. Initial estimates. Before we start with the demo, we need some initial estimates. How to get those? For PK, just typical, all of them are from NCA, volume of distribution, peripheral volume of distribution, clearance, and intercompartmental clearance. We get those from the NCA. For the Emacs model, the first 2, Emacs and EC50, you can easily get from the plot. And in this plot, we take it from the downswing arm because this is closer to equilibrium. So we can choose a value from here, maybe a little bit more than 1,000. For the Emacs, we have responses between 0 and 100, so no baseline, so Emacs shall be 100. For gamma and KE0, we just set initial values to 2 and 1. But what we also do is, once we set these values, we use the initial estimates tab in the Phoenix model to, get some closer values on the basis of the immediate display of the curve. So that's what it is right now. I guess we are now ready for the demo. Let me share my Phoenix application. So, okay, Chris, can you see it?
Yes, Bernd, everything looks good.
All right, thanks. All right, so here's the data. We've got some dosing data, just a single line. We said 69,000 units at time 0, and infusion, the duration of the infusion is 15 minutes. Here's the data, 3 columns, the time column, concentration and response. And as you see, for each response time point, we also have a concentration value. Let's send this quickly to a plot. So we just plot the data with time on the X, concentration on Y, and response on Y2. And here we are. Okay, we can maybe use a semi-log on Y. Maybe make this a little bit wider. Then you see the picture from the slides, so the concentration peak before the response peak. Maybe just one other plot for the hysteresis. Just need the concentration and the response. Unsort the X values and plot response versus concentration and put the X scale on log. And here you see our hysteresis loop. So this is the data. And what we said, we start with an NCA object since we want to get some initial estimates for our PK model. So here we just map time and concentration, CP. Takes the dosing directly from here, change it under the dose options, the bottom panel to IV infusion. Dose is dose, time of dose is time, and end time is length of infusion. That's it. We can execute the NCA object and get these parameters here, where we look at the volume and the clearance, which is roughly 2 and roughly 0.02. So we take those values and use that for the PK modeling part. We again send our input data to a Phoenix modeling object. Oops, come on. Here we are. And uncheck population, uncheck closed form. We want to have 2 compartments with an infusion, and we want to specify this with a duration. So time is time, CP is plasma concentration is concentration observed. This is a model. And we also can use the dosing table here. So dose is A1, time is time, and end time is A1 duration. So this is all set. We can just use the initial estimates tab. To specify the initial estimates. So we first need to change the time. These were 720 minutes. The volume should be roughly 2. Second volume, I don't know. Clearance was, I guess, 0.01 or 2. Second one's the same. This looks not too bad. Maybe we can increase this a little bit. Okay. Maybe also put it on a log scale, semi-log scale, so you can see the effect. Oops, it shouldn't go into the negative range. Something like this. Okay, should be good enough. This is a little bit steeper, but I'm sure the engine will do the rest, and we'll do the fit. Okay, here we are. This is a fit. Let's do a logarithmic scale. This looks good. Maybe a little bit overestimating here at the final data points. And do this a little bit wider. Okay. Yeah, it's a little bit overestimating in the terminal slope. Maybe we can change the residual error to a multiplicative one and do the fit once again. And this looks much nicer. You see that the data points are scattered around the regression line. That's good. Here are our values, which are nicely sharp. So this seems to be a good model. This is our PK model. And we take this, copy it and paste it back. And this will become our PK-PD link model. Okay. And what we said, we just need to change the type to PK Emacs. Let these things as they are. And we are just, let's look at the model. This is our current model where we just linked the PK model with an Emacs model. And now when we switch on this tiny box, it puts an effect compartment just in between. You can take it away, bring it back up, and that's it. Nothing else. So there are some warnings. We need to map the observations, the response observations. So let's do that. Go to main panel and map response to effect observed. And what we also need to do, we just need maybe the parameters. We can take the initial estimates from our PK model and say all, accept all fixed and random, and go to the initial estimates to see. Okay, so this is the C versus time plot, which shows a nice fit of the data, the PK data. Let's go to E versus time, the response, and you see we need to adjust a little bit here. We said EC50 is around 1000, Emax is around 100. And we need to also set the slope factor, gamma. So let's go back to initial estimates. And maybe use a little bit higher value. Okay, increase it a bit. Something like this. Okay, and now we can also look at a different plot, which is C versus E. This typically shows our hysteresis loop. Now we can adjust KE0, a little bit smaller here, something like this. And that should be it. Should be close enough for a fit. So let's do the fitting. Okay, here we are. What you typically do see with PK/PD models is that the response plots are really, because it has a uniform scale between the concentration response, and that doesn't fit, so you need to double-click on this plot to pop it out of the main window, and adjust the x-axis to autoscale best as well as the y-axis to autoscale best, and then you see both predicted actual values here. Let's have a look at those plots. And once again, we need to autoscale best. Okay, and oops, y shouldn't be log in this case to see the response better. So these are also nice fits. So this really shows that we have a very good model. A theta table with those values here and very sharp estimates. So this looks good. So with that, I guess we have just set up the PK/PD link model and fitted the data, and the results look good. So what we can do is we could use this model to set up a simulation with multiple infusions. So let's do a copy of this one, paste it back, and rename it to simulation. Okay. So what we do here is the first thing when you copy the model is to go to the fixed effects table and accept all fixed and random parameters. Go to run options, run a simulation. Here it asks for the number of points and the max X range. Let's say we can choose maybe 8,000 for 10 infusions, maybe 8,000 with 8,000 points. Y variables that we are looking to predict is concentration C, effect concentration CE, as well as E, the response. Now we need to specify the input, and here we can use the ADDL option, additional doses, where we just say add. We take a constant value of 9,000 units. The dose point, as we said, is A1. Oh, so sorry, this needs to go into the amount, obviously, and that is the delta time. The delta time is 720 minutes, 12 hours, and that's what it is. We just need to maybe remove this dosing panel and use an internal worksheet. So we use the infusion time, at time 0, and say we want 10 additional doses. Okay, and then we just run the simulation. And we will look at the simulation plot, which is here. Actually, there's no accumulation, so maybe 12 hours as an interval is maybe too long. Let's say we go for maybe 180 minutes, 3 hours. Then we don't need to run it that long, maybe 3,000 minutes. Run it once again. Okay. slight accumulation here. But these tables are, you just want to see them. You want to manipulate those. So what you can do is you can take this simulation sheet where you have all the data, send it to a pivot worksheet, and rearrange the data so that you have individual columns for the concentration, effect concentration, and the response. And that is by putting the Y1 name to the column header, to the column header, and the actual values to dV to values, and IVAR, this is a time as a row header. Let's do that. So we have now individual columns. This is a time and individual predictions. We can send this to a XY box plot with this to this, and it's to that. And we have it here as quick styles. We just want to unshow markers and get this nice plot. So in red, the observation, the response, and in blue and black, the concentrations. You can further, elaborate on those figures by, creating a hysteresis plot as well. But let's move on with some other options that what I presented in the slides. So we can take our PK/PD link model that we have here and copy it, paste it back to the workflow, and we first do the textual model. So this is this one. So we have this model, and we just move to the textual one. What we said here, we want to get rid of the structural parameters since we don't have any random effects. These are obsolete. So we just take fixed effects. We need to get rid of the TV in front of the parameter name. This is no longer a typical value. It's a fixed effect. Okay, this is it. And this is our textual model. Now we can introduce the delay statement. So we can copy this once again, paste it back. And this is then our delay model. Oops, can't write anymore. And so what we do here is we don't need this differential equation, but we replace it with just another statement, which is CE equals delay. And the delay from A1 plus the parameter T lag. And this we want to divide by V. Obviously, it complains that there's no T lag parameter defined. Okay, we just take the KE0 and change this one to T lag. And maybe as an initial estimate, we put in a 1. So that's it. We can do the fit here as well. It will do the same job, and this is a result. So it looks much the same, but this time using the delay in the differential equation. All right, here the thetas, the T lag is 1.8 minutes. Pretty sharp. So much, very close to the other figures. This was option 1. Option 2 was to turn the whole PK/PD model into a PD model. So let's take the PK/PD textual model and copy it, paste it back, and say this is our. It's no longer a PK/PD, it's a PD textual model. And here, what we can do here is we can get rid of all the statements about the two-compartment model. We just delete those. What we need to do here is we introduce the explicit concentration by a covariate statement. covariates C, and we need to, in this case, we need to define an effect compartment. So a deriv statement, C equals KE0 times C minus CE. Okay, and that's it. We don't need the observation and the residual error for the concentrations, and we don't need the 4 fixed effects here. See, it becomes a very short model in terms of coding. What does the warning say? Please remove dose worksheet. Yes. And map C. Yes, we have now a covariate C. We need to map CP to C in order to do that. And since we don't have any PK model, we don't need any dosing table, so we can get rid of that one as well. Let's have a look at the initial estimates. We need to go to E versus time. That's what it is. Looks good enough, so we can do the run and execute, and here's the results. Now we are only having the EOPS graphs because we don't model concentrations, and here's the fit with the theta values like here. Okay, and I guess that's all what I wanted to show in the demo. Let's switch back to the slides. Oops, come on. Okay. Here are the results once again. By the examination of these plots, you see we have a pretty good fit of the model to the data. And you can clearly see the delay between the plasma concentration and the effect concentration. Here you see the hysteresis loop, here the normal hysteresis loop in blue and the collapsed one in red. And this is the effect fit of the effect of the response. The parameters also, as we've seen in the demo, are very sharp, and so this is a very good outcome of the modeling. Let me summarize. So we have built an effect compartment model where we also introduced a new function of Phoenix 7.0, the delay differential equations. And I've also shown you how to turn the PK-PD model into a PD model by taking the explicit concentrations into account. And then we fitted all these models and examined the results. Also, what we showed in the demo was how to set up and run a simulation with multiple intravenous infusions. And here we have used the ADDL function. So this is, I guess, the end of my presentation. I guess it's now time for the Q&A. Chris, do you want to take over?
Sure, Bernd. Yeah. So we have some questions coming in, and if you go back maybe to the first question is related to your fitting, your model fitting. When should one use the closed form versus not using closed form?
Yeah, the closed form you can use whenever there is an algebraic solution available for your model. This might not be the case for more complex models. For simple models like one compartmental extravascular, or there's an algebraic solution available. So this is just how it is mathematically done. We here in our series, PML School series, just from the beginning on, wanted to deal only with differential equations. Therefore, we always checked off the closed form checkbox, because it's much more clearer if you are dealing with the formulas that you get from your references from books or publications. It's much easier to translate that into the, let me go back a few slides. As you see here, So when you're dealing with the differential equations, these are typically shown in references. It's much easier to transfer this formula into the PML code because you're just using it as is, instead of trying to determine an algebraic solution for those differential equation and use it in this way. So you can try and leave the checkbox on, but if there's no closed form available for a particular model, Phoenix will switch to a differential equation anyway.
Great, thanks, Bernd. The next question is related to when you're doing the PK-PD link modeling. And the question was that the PK parameters were not fixed in this case. They were copied from the PK run, but at the end of the day in the PK-PD link model, they were fit simultaneously with the PD. So the question is, when is it appropriate to fix the PK parameters versus fitting PK and PD simultaneously?
Yeah, that's a good one. I mean, this is also when you look at this. I mean, this is really at the extreme of two things, right? If you are having concentrations at any measurement time point of the response, you actually don't need a PK model to come up with a PD model, because at the end of the day you are interested in your PD parameters. So this is the one extreme, and the other extreme is to try to fit everything with a model, the PK data as well as the PD data, and this can become a problem when you are having too many parameters that could be changed. That change, for example, in this case, how many parameters we have? 1, 2, 3, 4, 5, 6, 8. Just eight parameters. And if you want to find good final estimates for all of these 8 parameters, this could be a too complex scenario for the engine. You would need to have very good initial estimates to get to really a global minimum, because what you're creating is a hyperdimensional plane where you try to find a global minimum, and if you are too far away in such a complex scenario, you might get trapped in a local minimum. So, and that's the typical scenario when you want to first find estimates for the PK parameters, right? These might be, in this case, only 4. So you might be more. The chances are that you find a good model for these 4 parameters for PK only. Then you freeze those, so you don't let them change while fitting the 4 PD parameters. It just increases your chances in finding the best model. So it's really a modeling strategy. You need to assess the data that you have. How easy or how difficult it is to find good fits. In this case, the fits looked just nice, so we were pretty confident that we could we wouldn't miss the global minimum, the best model. But in real cases, if you will, it might be much more difficult to find good initial estimates and really be convinced of the final estimate that this is really truly the best model. So you have to come up with different scenarios, and here I've given you the 2 extremes: fitting all parameters, PK and PD parameters at once, or just using the concentrations itself themselves as and not modeling the PK part anyway, and just focus on the PD part.
Thanks, Bernd. We have one more paired question. This is related to the new delay statement. The first part of the question is, does the delay statement operate the same way as the effect compartment? Is the underlying math the same? And then coupled with that, can the delay statement be used with PD compartments as well as the PK compartments?
All right, maybe first answer to the second one, because that's the easier one. You can use the delay statement everywhere. I mean, for PD compartments as well as PK compartments. So you just need to have a differential equation, and then you can use the delay statement within those. The math is different, is completely different. So the effect compartment uses a differential equation, right, to come up with a KE0, zero order rate constant. This is completely different to a T-lag parameter. So it's really a different mathematics behind it, and maybe because we are going into deep mathematical formulas or concepts, we might be writing up a more detailed answer to these questions in the Q&A that we will post to the forum later on.
Great, thanks, Bernd. That's all of the questions. As Bernd alluded to, we will post the answers covered here as well as any additional questions on the Certara forum as usual.
Okay, thanks, Chris, for the Q&A. Before we close, here's what is coming up next. I know I've highlighted this webinar quite a few times, but since we've been dealing with a distributed delay in today's seminar, I thought it would be worthwhile to remind you of this opportunity once again. So there's on the 16th of May, Wojciech Krasansky is giving a very interesting topic, a lecture on a topic, modeling PK/PD systems with distributed delays, which is an ideal opportunity for you to expand your knowledge on this topic with the distributed delays. So you shouldn't miss that. And finally, in 2 weeks' time, it's again Chris Mail who will do the next presentation of the PML School series, Turnover Model 1 IV bolus dosing. And this is really a truly classic one because it's dealing with a warfarin-PCA interaction, a must-watch webinar. So I hope to see us there. I mean, with that, I want to thank you all for your continued interest, and we will see us again on June 8th, the latest. Thanks and goodbye, and you may disconnect now.